Hello everyone, I'm Zhihao Zhang from Tsinghua University. I will present our work PlanB efficient software IPv6 lookup with linearized B+3. This research is conducted by our team from Alibaba Cloud, Shanghai Jiwu University, Xiamen University, and Tsinghua University. And the global adoption of IPv6 is increasing. Statistics from Google show an increase in IPv6 user size from 20% in 2019 to 50% by 2026. This data indicates a continuous shift in network traffic from IPv4 to IPv6 across the internet. And countries and regions facing IPv4 address shortages currently have the most urgent need for IPv6 transition. Associated with this traffic increase, the forwarding information bases, or FIBs, in global routers are expanding. Data size from ripe root collectors document a continuous growth in aggregate prefix counts over recent years. In addition to expansion, the distribution of prefix lengths is skewed. A small group of specific prefix lengths, such as 48, 32, and 40, dominate the tables, accounting for up to 8% of our routing entries. And IP lookup determines the next hop forwarding path by finding the longest prefix match, or LPM. The developers must choose between hardware and software, LPM. Hardware processing using TCAMs, ASICs, or FPGAs offers high throughput. However, specialized hardware has high monetary costs, consumes more power, and lacks the necessary flexibility for software-defined networking and network function virtualization. Conversely, commodity software processing on general CPUs provide flexibility and reduced cost, but the LPM operation creates a severe CPU bottleneck during IPv6 by packet processing. Transitioning from IPv4 to IPv6 causes a target performance reduction in existing software algorithm, including both trie-based and hash-based methods. Because IPv6 addresses are 128 bits long instead of 32 bits, memory footprints expand by 10 to 50 times. The expanded data structures can no longer fit within the limited capacity of the fast SRAM on the CPU cache. Data spills over into the slower main DRAM space. Deeper trie structures and more memory accesses lead to L3 cache misses. As a result, IPv6 lookups are 3 to 10 times more computationally expensive than IPv4 lookups. The core issue limiting performance is the mismatch between the lookup problem dimension and the algorithm. LPM is inherently a two-dimensional search process, requiring the method to match the prefix value and then determine the maximum prefix length. Existing algorithms treat LPM as two separate one-dimensional search phases. Trie-based methods traverse the address space bit by bit. This creates a deep data structure that enforces frequent memory indirection. And hash-based methods probe multiple hash tables sorted by prefix length. This approach is susceptible to table collision and like bounded worst-case execution times. To resolve these issues, we designed PlanB to provide high-speed IPv6 lookups on commodity hardware. The system design is divided into 3 components. First, dimensionality reduction transforms the two-dimensional LPM process into a one-dimensional elementary interval search. And second, we organize a search space using a cache line, linearized, and pointerized B+3 data structure. Third, we employ a hardware symbiotic search logic utilizing vectorization, batching, branch-free, and loop unrolling. Step 1 in our design is range conversion. We flatten the two-dimensional prefix space into a set of deterministic boundaries. Every routing rule defined by a prefix and a length is mathematically converted into a closed IP address interval containing a start address and an end address. And in this model, prefixes are overlapping rectangles where the prefix length acts as a priority metric. Following conversion, we perform one-dimensional interval partitioning. We collect and sort all the start and end boundaries. These sorted boundaries are used to partition the entire 102 and 28-bit IPv6 space into a complete array of non-overlapping elementary intervals. The system assigns a definitive next hop to each interval based on the highest priority prefix. The two-dimensional search problem is now a one-dimensional array predecessor search on this interval site. Moving to step 2, we must efficiently navigate this one-dimensional array. A standard flat array B tree organized search node in a continuous array. However, using this standard layout requires the processor to verify if the search target is found at every internal node during traversal. These checks introduce conditional branches in the control flow. A conditional branches lower CPU pipeline efficiency and make single instruction multiple data or SIMD difficult to implement. And therefore, we utilize a modified layout called the linearized B+ tree. Data is separated so that internal node only guides the search, and the actual interval keys reside entirely in the leave node. This array is pointless. The positions of child nodes are calculated using arithmetic on array indices, specifically adding child offset to level start positions. We also tune the parameters so that each node aligns with a 64 by CPU cache line. For example, the 864-bit case construct a 9-array tree block where each node perfectly occupies one cache line. In step 3, we optimize the search execution. A standard search applies a sequential scalar comparison for each element in a node. PlanB instead uses a data-level vectorization from SIMD instruction. And PlanB utilizes AVX 512. And PlanB also supports other vectorization like AVX2 and ARM-Neon. The algorithm broadcasts the incoming target IP addresses into all slots of a 512-bit register. It then loads the 8-node keys from the cache line into a second register. And then the processor compares all 8 keys against the target address. To determine the next step in the tree without stalling the CPU pipeline, we develop a branch-free traversal. A CPU branch means prediction cause pipeline to flush, costing dozens of clock cycles. PlanB eliminates if and else jumps entirely. The vectorized comparison step outputs an 8-bit mask instead of a Boolean value. And then PlanB runs a population count instruction on that bit mask. The numeric result of the pop count accurately produces the integer index of the next child branch to fetch. And we further increase processor utilizing by implementing batching and loop unrolling. By performing independent lookups in batches, PlanB pipelines operations to hide the multi-cycle latency of SIMD comparison. instructions. Additionally, the linearized B+ tree guarantees bounded depth. For example, 1 million intervals require a maximum of 6 to 7 tree levels. Because the loop count is known, the compiler fully unrolls the search traverse loops at compile time, reducing loop control tracking overhead. And network environments require dynamic FIB updates. PlanB handles modification utilizing a background rebuild and atomic swap mechanism. Secondary CPU core processors process the new rule list to construct new one-dimensional interval structure and linearize B+ tree in a separate memory region. Upon completion, a single atomic pointer swap updates the system to direct new lookup traffic to the update tree. This ensures zero lock condition on the active search path and provides deterministic update times. The old tree is subsequently delocated. And we integrate PlanB into DBDK environment to handle packet input and output. We configure an RX LPM and TX pipeline in DBDK. Lookup modules are pinned to a single CPU cache group, such as an isolated core complex on AMD hardware. Decoupling the general packet L threads from the memory-intensive IP routing threads ensures that the linearized B+ tree data means residency in the L3 cache without evacuation from other system tasks. We test PlanB systematically on two platforms, a 24-core Intel server and a 12-core AMD Ryzen 9 processor. The inputs consist of 14 real-world FIB datasets collected from the RIPE and RootView projects, and 4 synthetic FIBs scaling up to 1 million prefixes. We benchmark PlanB against state-of-the-art software methods, including trie-based method and hash-based method. And the result shows improvements in both system throughput and single-core lookup speed. And in the DBDK test for L3 forwarding throughput, PlanB certain processing rates 1.7 to 5.8 times faster than the baseline on the Intel server. And in the single-core test, PlanB reaches a peak speed of 390 million lookups per second, or MLPS, on the AMD CPU, testing 1.6 to 12.5 times faster than all other algorithms. And we also test multi-core scalability by enabling additional processing cores sequentially. As shown on the figures, PlanB achieves near linear scalability on both processors. On the AMD platform, the aggregate speed reaches 3.4 million lookups per second, or BLPS, across 12 cores. On the 24-core Intel platform, parallel speeds scale up to 4.6 BLPS. And then PlanB also reduces FIB memory overhead by 56 to 92%. The entire searchable array for 1 million prefixes occupies about 36 megabytes, and allowing the entire routing table to fit inside a standard L3 CPU cache. Additionally, because the pointless array requires no complex dynamic memory allocation, and the system updates are faster, the computational cost of running background rebuild is amortized by the speed of execution. We perform an ablation study to show the origin of our performance gains. A simple baseline sequence using standard binary search results in 10 MLPS, and adding the linearized B+ tree generates a 3.8 to 4.6 times gain. And including AVX 512 SIMD comparison provide an additional 2 to 2.7 times multiplier. And adding batching and loop unrolling provide a final 3 to 4.5 times boost. And step by step, the combination of these techniques directly as the final 390 MLPS processing rate. And PlanB is easily adapted to diverse hardware platforms such as FPGA and ASICs using on-chip SRAM. And it functions efficiently even without advanced SIMD. PlanB delivers a near constant throughput and remains resilient under unpredictable traffic patterns or malicious attacks, guaranteed by fixed and shallow search depths. And PlanB also supports hybrid control data plane architectures, allowing control processor to handle background tree reconstruction while other processors perform high-speed data plane lookups. And to conclude, the performance problem in current lookup technologies is defined by treating the two-dimensional prefix-based search as two inefficient one-dimensional processing steps. And our insight is that two-dimensional search over two-dimensional prefix matching can be unified into a single one-dimensional search over non-overlapping address boundaries. And our solution, PlanB, applies a linearized B+ tree enhanced by SIMD and batching, branch-free logic, and loop unrolling. And our results show that PlanB improves throughput and also reducing the memory footprint. Thanks for your attention, and our open source code for PlanB can be inspected as the GitHub repo.